All right, so does anybody see anything that they feel they could use some assistance with regard to this homework assignment, other than I think problem 7, which is specifically a multi-frequency circuit, which is what we're going to talk about today after we kind of wrap up regular old solid, steady state sinusoidal circuit analysis. So much alliteration. Anybody got anything? All right, well, then we're probably going to get out a bit early today. Oh no. All right, so let's consider what happens when we have a circuit that is being excited at multiple frequencies. So a simplistic example of this might be something, let's see. Let's call this guy Vs of t. Call this guy Is of t. And let's make this. All right. And our ultimate goal, let's say, is to determine the voltage drop over our capacitor, Vc, as a function of time. And I'm going to say that Vs of t is 10 cosine 2t volts, and Is of t is 2 cosine 5t amps. So there are two different sources in the circuit, and they are operating at two different frequencies. So what does that mean with regards to the impedance of our, say, inductor or capacitor? So as a refresher, the impedance of a resistor is the resistor value itself, so it should be entirely unaffected being placed in a multi-frequency circuit. The impedance of an inductor is given by J omega L, but we have two different omegas. So the circuit cannot have, like the inductor cannot represent two different impedances simultaneously. Similarly, for our capacitor, we have 1 over J omega C. Well, we have two different omegas, so the capacitor would also have two different values for its impedance. So how we're going to be forced to analyze any circuit containing capacitors or inductors that is excited at multiple frequencies is by using simply superposition. If we turn off all the sources associated with one particular frequency and analyze it with the others, we should be good to go. So in this case, let's turn off current source and on the voltage source in the frequency domain specifically. So with the current source off, that means we're going to replace it with an open circuit. Here is our voltage source. Then we have our inductor And here is our capacitor. Because we're going to be working in the frequency domain, we need the frequency domain or phasor representation of our source voltage. So that should be what? How do we convert Vs of t into a phasor? What was that? 10 angle 0. Yeah, easy enough. 10 angle 0 degrees volts. Our resistor, as stated previously, will continue to be a 10 ohm resistor. Now our inductor, so we have J times omega, which in this case is 2, times L, so which is 2, so that's J times 2 times 2 is J 4 ohms. And for our capacitor, we have 1 over J omega C, so that's, let's see, omega is 2, C is 1/5, so that's 2/5. Reciprocal of that is minus J to the 5 halves, or minus J 5 halves, minus J 2.5. Our phasor voltage, VC, is like so. So how can we solve for that? So we can use voltage division to get it directly, or we could do KVL solving for the current. Absolutely right. So let's use voltage division to get it in one step because I'm lazy and it's less work. So from this, VC is simply going to be our source voltage, 10 angle 0 degrees volts, multiplied by the impedance over which we want the voltage drop. So that's minus J 2.5 ohms, divided by the total series impedance, which is going to be 10 plus J 1.5 ohms. So that's me combining the resistor and then the impedance of the inductor and the impedance of the capacitor into one single thing. And so this will give us .472 with an angle of negative 98.531 degrees volts. Easy enough, right? For our next step, we would turn on the current source and off the voltage source. Sorry. So that would mean that sorry about that. Here's what our circuit looks like. We need to use the phasor domain representation of our current. So if it was 2 cosine 5t amps, it should look like 2 angle 0 in the frequency domain. Our resistance stays the same because omega is now 5. That means that our inductor has an impedance of J10. And our capacitance should have an impedance of minus J1, if I'm not mistaken. Let's do the math. My argument there is that if I increase the frequency by a factor of 2.5, then that should decrease the impedance of my capacitor by a factor of 2.5. So let's do the math on that real quick. So 5 times 1/5 is 1. So we have 1 over j, which is the same as negative j. So that is correct, negative j1 ohms. Let's put prime here. So how might we go about solving for that capacitor voltage in our second instance where the current source is on and the voltage source is off? So we can do current division to find out how much current is flowing through that right-hand branch, and then Ohm's law on top of that to get the voltage drop specifically. So I'm going to do that all in one single equation. So I'm going to say that VC double prime is going to be, let's see, so we're going to have 2 angle 0 degrees amps. Then I'm going to have, let's see, 1 over J10 minus J1 is positive J9 ohms. So that's the total impedance seen in the right-hand branch divided by 1 over 10 ohms, which is the impedance of the left-hand branch, plus 1 over J9 ohms, which is the impedance of the right-hand branch again. That gives me the current flowing through the right-hand branch, and then I multiply that by minus J1 to give me the voltage drop. So that's current division and Ohm's law wrapped up in one single equation so that we can do less work. I get 1.487 with an angle of negative 131.987 degrees volts. So finally, we need to tie everything together. Our ultimate goal is to find out what the time domain voltage across our capacitor was. All right, we look up here at our original circuit. We're trying to find VC as a function of time. This is a place where you could easily make a mistake, okay? So in our DC circuit analysis, we found that if we take, if we find the response with, you know, one source on and the other source off, and then we flip those conditions, we can simply add the results, right? The problem here is that we are going to do that, but we're going to add the results only in the time domain. We cannot simply add the frequency domain results together, meaning I can't say that the voltage drop over the capacitor is 2.472 angle negative 98.531 degrees plus 1.487 angle negative 131.987 degrees, because those two phasors represent quantities at different frequencies, right? I can't add those two different frequency terms together and just say I get a generic answer. So I have to go back to the time domain and then add those time domain results together. So from that, VC of t is going to be 2.472 cosine 2t minus 98.531 degrees plus 1.487 cosine 5t minus 131.987 degrees. That's it. So any multi-frequency circuit you have, you simply analyze the circuit at each of the specific frequencies and then add the time domain results together. In practice, where do you think you might find circuits that have excitations at multiple frequencies? Anybody have any thoughts or anything like that? So you're saying transient analysis with a sinusoidal system? Yeah, I mean, to some extent, yes, but that's really, like, you can definitely have a circuit that changes between two different points of sinusoidal steady state, and it will have a transient response. Largely, that is going to obey, like you're going to use Laplace transform and stuff like that, just because the math gets really gnarly trying to do everything in the time domain there. But that's not really a multi-frequency circuit necessarily, unless you happen to have your sinusoid excitation being two frequencies and then the same two frequencies after the transient occurs, right? But think about a radio, all right? So radio, how many of you guys know how radio signals or anything like that are received or sent? Anybody have any clue? So the audio signal that we hear from the speakers in our vehicle, or if you're old like me, a boombox or whatever, what range of frequencies do you think that is? What range of frequencies can a human hear? Anybody have any ideas? Yeah, so it's so the telephone system or landline telephone systems uses, I think, 400 hertz to 4 kilohertz, which is actually really low. That's why if you ever hear hold music, it sounds so awful, and it's because all of the lows have been eliminated and all of the highs have been eliminated as well. That's why holding music sounds like crap, is because they literally cut off all the interesting parts of the music. Standard human ears are somewhere on the order of a few hertz. I think like 15 hertz would be considered a sub-audio frequency, but it's really close to the threshold, and you can hear up to somewhere around 20 kilohertz, thereabouts. People with better ears than mine can hear higher, but it's somewhere around, 25 hertz to say 25 kilohertz or so. What signal or what frequency are radio signals broadcast at? Anybody got any idea? So let's talk about like an FM radio. What does KLPI's station identification of 89.1 mean? 89.1 megahertz, absolutely right. So we have a carrier signal that's being broadcast at 89.1 megahertz, and then a message signal that consists of significantly lower frequency information that is what we are able to hear. That is an example of a multi-frequency circuit. There's also, and this is specific to Japan, they have frequency conversion stations because there's a river that effectively runs through the middle of their country. Half of the country, I believe the left half of the country effectively runs on 50 hertz, and the right half of the country runs at a frequency of 60 hertz. And it's because of how the country was segregated after World War II. And the places where America helped rebuild the infrastructure did everything at 60 hertz, and the places where Europe helped rebuild the infrastructure did everything at 50 hertz. And they had to come up with a way to be able to send power from one portion of the country to another. So they have frequency conversion stations that are all based on multi-frequency circuits and being able to send power back and forth between these two different operational frequencies. So this seems rather trivial, does have a significant application. And then when we get into filter circuits, after we cover steady state sinusoidal power analysis, that is all about how a particular circuit behaves at multiple frequencies and how you can manipulate impedances to either pass signals or cut off signals appropriately, all as a function of frequency. Okay, so I've talked for 25 minutes. I don't know what else to talk about today, or we're going to get even further ahead than we currently are. So if you guys want to call it a day, I'm good with that. If you want to talk about more stuff or review anything, I'm good with that. If you want to push forward, start covering power, that's my least favorite option, but I'll do it if you want me to. Sure. Okay. Right. Today is when it's supposed to be turned in, right? At 5. Okay, so there's still some time left. All right. Sure. Okay.
Well, I have an integrating OpEx. I know that you're supposed to be, the gain is used by, found by capacitance, resistance.
Okay.
As long as the resistance, capacitance, both multiplied together by 1, so let's say the resistance was 10K ohms and the capacitance was 0.1 milliohm or millifarads. It would be 1 over 1, so it would be 1. But I ended up having to find a very arbitrary capacitance.
So when you take the integral, is it a sinusoidal function or exponential function? Because you also have to keep into
It was a square wave.
Square wave to a triangle wave.
Let's say I was turning.
Oh, okay. I know what you're talking about now. Let me look at that problem real quick. Error. Exam 1 take-home portion. All right. So
I don't know if I'm just having a problem with like understanding how the integrated works.
You're not necessarily. So you're talking about your problem too, where you're asked to design a multi-stage op-amp network, which will convert a 1 volt peak-to-peak sinusoidal input into a 1 volt peak-to-peak square wave and a 1 volt peak-to-peak triangular wave. So one thing that you need to recall is that it takes time for your capacitor, if you're doing an integrator circuit, to fully charge and fully discharge. And that time constant is simply going to be RC. So if I want, I believe I say I want a frequency of 1 kilohertz, that's going to inform your decision on what size of resistor and capacitor to use, because you need RC, the product of R and C, to be on the order of 1 millisecond, I believe, with a 1 kilohertz frequency. If you have it too short, so if you size your components incorrectly, you're never going to fully charge or discharge, and so you're going to see that it constantly kind of builds up and looks weird.
Right.
Right. Yeah, so you need to adjust your component values to take into account the fact that it takes time for the capacitor to fully discharge. Because the only way you're ever, I'm assuming that you're starting with the square wave and integrating it to get the triangular wave, right?
Right.
Which you can get the square wave from the sinusoidal wave by using a comparator pretty easily. So yeah, the only thing that you really need to pay attention to there is sizing your components in such a way that it allows time for it to discharge so that it falls down. It doesn't rise and then drop a little and then rise and then drop a little and then rise and drop a little. It should be going up, falling down.
Yeah.
Yep, so you just need to resize your components to achieve this specific frequency.
Now, is there a way that, is there a formula for you be able to calculate that? Or you just
Tau is equal to R times C. It's an RC circuit. Right, so the time constant is literally.
Oh, so you just have to have RC tau.
Yeah.
Okay,
or somewhere around there.
The
no. So the gain, you need to meet both criteria because you want it to be a 1 volt peak to peak signal, which is going to have something to do with the gain, but you also need to incorporate the time constant because you need the signal to be able to decay so that you don't get what I'm assuming was looking something like that.
Yeah, that's exactly what.
My question is, obviously, in the beginning, you're gonna have a part where it's fast charge, right? So
Okay.
the initial in the middle of it, it's gonna, it should start out slow, basically almost at zero, then build up, and drop down, and slowly get to the point where it's at a one, right? Or, well, not a one, but a half to half.
I got around that.
You know what I mean?
I don't know what you mean by half to half there, because so you're not going to see an exponential.
Positive half an amp.
You're not going to see an exponential response because you're not looking at a transient here. So it should be fairly linear. I mean, there might be a little, like a small curvature, but it should be a fairly linear triangular wave where, let's just say, I don't remember off the top of my head if you're going to wind up with a DC offset or not, but it should be something like, this is 1 volt, here's 0 volts. Literally a series of triangles just like that. So it should not, I believe, do that. Oh, well, if it does that, then that's fine. I may be misremembering here. Actually-
I use -0.5 to 0.5.
That's what I was gonna say, mine was top one.
Yeah, now I'm thinking of it. So when it goes, okay, so when it goes negative, so when your input signal switches from positive to negative, you're taking the integral of a negative number, a negative constant, which means you should have a negative slope. So it should be like this, not like this. That's right. It should be like this guy up here. Sorry, that's my fault for misremembering things. With a goal of it having a peak-to-peak value of 1 volt, which means it could be half a volt here and negative half a volt here, or you could have this whole thing shifted by half a volt and it ranges from 1 to 0. If its peak-to-peak value is 1 volt, I'm happy. I don't care whether or not it has a DC offset, if your methodology happens to give it one. Yes?
Is it correct to use an initial thing?
Initial condition, absolutely. The only way to get around having that would be to put a resistor in parallel with the capacitor in your integrator to effectively make sure that it burns off the energy, but that makes the math way harder. So just set initial condition to where it starts at 0 energy or something like that, and I'm good.
Well, I'll just
That's much easier to figure out what's going on.
The max.
Okay. Yeah. Yes. Exact same thing as the homework format, except call it exam 1 or whatever. Yeah. Any other questions? All right, I will see you guys on Friday where we're going to talk about instantaneous power and average power, and if I have time, maximum average power transfer in steady state sinusoidal circuits, which I believe should be new to you. The instantaneous power and the average power stuff is straight review from circuits 1. So I'm probably going to go through that reasonably quickly. All right, you guys have a good rest of your day.